You ever find yourself in a discussion and you just know you and the other person are saying the exact same thing, just with different words? Language can be a bit slippery, a little ambiguous sometimes. But what if there was a way to be absolutely 100% certain that two statements mean the same thing? Well, there is. Let's dive in. So let's take a look at a real puzzle. We've got two sentences here. On the surface, they look pretty different, right? They use different words. One's kind of positive, the other is framed in the negative. Now, your gut might tell you one thing, but logic gives us the tools to prove it, with no doubt whatsoever. All right, here are our two contenders. Statement A, pretty straightforward. If I eat this giant cookie, then I will feel sick. It's a simple cause and effect prediction. But then look at statement B. If I don't feel sick, then I didn't eat that giant cookie. It sort of looks at the whole thing in reverse. So the big question is, are they just two sides of the same coin, or is there a tiny difference in meaning? That's the puzzle we're going to solve. To crack this puzzle, we need to bring in a really important concept from the world of formal logic. You could say it's the key that unlocks this whole thing. And here it is, logical equivalence. This is our gold standard. It doesn't just mean two sentences are kind of similar. No. It means they are perfectly one-to-one interchangeable. If one statement is true, the other has to be true. If one is false, the other has to be false. Every single time, no exceptions. So, how do we actually test for this perfect interchangeability? Well, we've got a seriously powerful tool for the job called a truth table. Think of it like a logical laboratory where we can test our sentences under every possible scenario and see if they really do behave in the exact same way. Okay, time to get our hands dirty. Let's actually build a truth table from the ground up for our two cookie statements. It's a really neat step-by-step process that just strips away all the confusing parts of language and leaves us with pure, simple truth. We're just going to follow this simple 5-step plan. First, we break our sentences down into their basic parts. We'll let P be, I eat a cookie, and Q be, I feel sick. Then we'll figure out the truth value of our first statement, if P, then Q. That little arrow just means then. Next, we need the opposite of our basic parts. Logicians call this a negation, and they show it with this little squiggle, the tilde. After that, we can evaluate our second statement. If not Q, then not P. And finally, the moment of truth. We just compare the final results. And voila! Here is the completed truth table. Now, just focus on those two highlighted columns. The first one shows the truth values for, if I eat the cookie, then I will feel sick. And the second one is for, if I don't feel sick, then I didn't eat the cookie. Just look at them. True, false, true, 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 false, true, true. The pattern of trues and falses is a perfect mirror. They are absolutely identical in every single scenario we could dream up. And there you have it. That's our proof. The two sentences, despite sounding so different, mean the exact same thing. They are logically equivalent. And by the way, this specific move, where you flip the two parts of a statement and negate them both, it actually has a name. It's called the contrapositive. And a statement and its contrapositive are always logically equivalent. Pretty cool, huh? Now, I know what you might be thinking. Building a truth table every single time you want to check if two things are the same, well, that would get old pretty fast. But don't worry, generations of logicians have already done all the heavy lifting for us. See, they've established a whole set of fundamental laws of logic. The best way to think about these is as proven, totally reliable shortcuts. You can use them to move things around, simplify, and compare logical statements with total confidence, and you never have to draw a single table. Let's just take a quick peek at a few of these workhorses of logic. Real quick, this first symbol, the wedge pointing up, just means and. The one pointing down means or. So the commutative law, it just says that for and or, the order doesn't matter, just like 2 plus 3 is the same as 3 plus 2. The associative law says you can move the parentheses around, and the distributive law, well, it works almost exactly like it does in basic algebra. These are the rules that let us legally rearrange logical sentences. Now, among all these laws, there's a special pair of rules that are so incredibly useful and, well, elegant that they really deserve their own spotlight. They come from a logician named Augustus de Morgan. Okay, I know, that sounds like a real mouthful, but it's actually an incredibly powerful and simple idea once you break it down. In logic, a conjunction is just a fancy word for an and statement, and a disjunction is an or statement. De Morgan basically gave us a perfect, foolproof recipe for handling the word not when it's in front of them. So here are his two laws in their symbolic form. That little hook symbol just means not. The first one shows us what to do when we're negating an and statement. The second one shows us how to negate an or statement. See that pattern? The not basically gets pushed inside to each part, and the connector in the middle, the and or the or, flips to the other one. And here it is in plain English, which makes it so much clearer. So, for example, think about the opposite of it's cold and it's raining. Your first guess might be it's not cold and it's not raining, but that's wrong. De Morgan's law tells us the true opposite is it's not cold or it's not raining. This is a super powerful tool for avoiding really common logical mistakes. All right, let's look at one more absolutely essential shortcut. This one is for negating an if-then statement. It seems like it should be easy, but you'd be surprised how often our intuition gets this one completely wrong. So take a look at this sign. What is the actual logical opposite of this statement? A lot of people might guess something like, if you don't park here, then you won't get a ticket. But that's not it. Let me ask you this. What would it take to prove this sign is a lie? The formal rule looks like this. The negation of if P, then Q is logically the same as P and not Q. I'll admit, this is probably one of the most useful but least intuitive rules in all of basic logic. And here's why it makes sense. To prove that original statement false, you have to do two things. You have to satisfy the if part, and you have to violate the then part. The only way that sign is lying to you is if you actually park there and you manage to not get a ticket. That single situation is the true logical opposite. So, okay, we've built some truth tables, we've learned some really powerful laws of logic, but why does any of this really matter when you're not in the logic class? Well, because this isn't just some abstract theory. This stuff is the invisible engine that powers our entire modern world. The logic gates inside your computer, the algorithm behind a search engine query, even the way a lawyer structures a rock-solid argument, they all run on these exact same principles of equivalence and logic. It's the very architecture of clear, precise thinking. And really, that's the big takeaway. Mastering these rules does so much more than just help you solve puzzles. It actually trains your brain to think with more clarity and more precision. It helps you see the hidden structure beneath the surface of arguments, which lets you spot the weak points in other people's reasoning and build your own ideas on a much stronger foundation. So, we've just added some seriously powerful tools to your mental toolkit. The only question left is for you. Now that you know what to look for, where are you going to see this stuff at play in your world? Maybe in a news article or an ad on TV, or just a conversation with a friend. Keep an eye out. You'll start seeing both the elegant beauty of sound logic and the clumsy missteps of flawed reasoning everywhere.